Okay guys, we're going to move on now to chapter 6, which will give us an opportunity to delve a little bit deeper into Newtonian mechanics. This is a chapter that I hope that you guys are going to find to be a lot of fun. I think it's a cool chapter. We can get into some really interesting problems involving Newtonian mechanics, and we can see just how intricate this really pretty simple framework is, right? Newton just says F equals ma, and as we've already seen, there's a lot to F equals ma, and we're going to see that there's even more. Where I want to start today, or in this video, is to talk about friction. And friction is a really important concept, and a really interesting one, I think, as well. Let's make sure we understand what we're talking about here. In particular, in this chapter, we're going to think about sliding friction. There are other types of friction, but I'm going to think about sliding friction, which is the friction or the resistance that occurs when you try to slide two surfaces past one another. And we know that there is this resistance, right? We see it in our everyday lives. We feel it in our everyday lives. If I attempt to push an object across the floor, there's resistance to that pushing, right? If you have your couch on the floor and you're trying to push the couch aside, you have to overcome some resistance between the couch and the floor. And it might be worth starting by thinking about why there is such a resistance to sliding. So where does this resistance to sliding come from? And in some cases, it's really easy to see where this resistance comes from. For instance, if you try to rub your hands together, right? If you put the two palms of your hands together, you can feel the resistance, right? You can sense that resistance, and it's not hard to see where it comes from. You look at the palms of your hands, and you see these little lines on your palms, these what are called friction ridges that you have on your palms. That when you're trying to slide your hands past one another. If this represents, this is supposed to be the surface of one of your palms, right? It's not smooth, it's rough. And if this is the surface here of your other palm, you can see that there are these little bumps, these ridges. And when you try to slide your palms past one another, if you try to move your palms past one another, there's going to be some interlocking of these little bumps. And as you slide your hands past one another, these bumps have to overcome one another. You have to force these bumps to slide past one another. So there's some obvious resistance there. It's a little less obvious, though, if you imagine, what about another case where, let's say, we've got a smooth tabletop here. So this is supposed to be a nice smooth tabletop. And maybe I take a book, a nice smooth hardcover book, and I put it on the tabletop. So here's this book. And so I've got a smooth table and this smooth book. And then I go ahead and I push the book, right? And so I apply some force to it. And if I don't push it hard enough, the book doesn't move. And the reason the book doesn't move, of course, isn't because there's some magical hand pushing back against me. It's that there's some resistance here to the sliding, but it's hard to see where that resistance comes from. So there is this, in fact, you push forward, let's call that P, and there is now some force of friction acting backwards. So I'll write that as F, some friction acting backwards. But of course the book is smooth and the table is smooth, you say, but maybe you can imagine with a little bit of imagination that if I took a little piece here and I blew it up really big, that I would see that this smooth book is in fact not smooth on the microscopic level, it's bumpy. And the smooth table is in fact not smooth on the microscopic level, it's in fact bumpy. And so on a much smaller scale than, say, your palms, on a much smaller scale, there is still this roughness to the book and a roughness to the table. So there is, on the microscopic level, this same resistance. We could go even further. You could imagine on an ultra microscopic scale, what if you had two surfaces that are remarkably smooth? Well, there's actually an interesting phenomenon that might be worth mentioning, which is called cold welding. Okay, welding welding is a term that's usually used for when you heat metal up. The metal will melt, and then if you put two pieces of this molten metal together, the metal will weld to itself or fuse with itself. Cold welding is an interesting phenomenon. If you take two ultra smooth pieces of metal in a vacuum so that they're perfectly clean and perfectly smooth, and you put those two pieces of metal together, they will instantaneously weld to one another and become a single piece of metal, such that you can't in fact pull them apart. This is a known phenomenon. It's used industrially on the nanoscale to put together small pieces of metal, to weld them together without using heat. You can actually force two pieces of metal to become welded into one. And the reason is that on the ultra microscopic scale, atoms can actually become attracted to one another. So this is atomic attraction. I'm not really doing this concept a whole lot of service here, but there's some atomic attraction that can occur. And so even if you have really smooth pieces of material, ultra smooth pieces of material, you're still going to have resistance, because you're still going to have these atomic level attractions that go on. That's called cold welding. So suffice it to say, there is, no matter how smooth a surface you have, there's going to be some resistance to sliding two surfaces past one another. It's sort of a fact of life. This friction is going to exist. Now, here's another interesting thing. Let's go back to the example of a book on the table, right? Let's say we've got, I'll draw it right here. Here's the table, and here's the book, or block, whatever this thing is. And I go to push this thing. And let's say I push it with some force P, and it doesn't move. Why doesn't it move? Well, it doesn't move because a force of friction now acts, which is equal to P, right? These two are equal, which is why the block doesn't move. Well, what happens if I push a little bit harder? What happens if I make this P a little bit greater? Well, it still doesn't move. What now has happened? Well, as I've increased P, so too has F increased. And again, now they're still equal, because the block is still in equilibrium. It still hasn't accelerated. So the force of friction is equal to the pushing force. So as I keep pushing harder and harder and harder, the friction force grows. It gets bigger and bigger and bigger. And then I reach, actually before I move ahead, let me point out that at no point here does the friction force become bigger than the pushing force, right? Friction will never produce motion, right? It's always going to resist motion. So at no point does the friction force become greater than the pushing force. If that happened, that would mean that I push the block forward and it accelerates backwards, which isn't going to happen in this case. But you can see what would happen is eventually, if I push hard enough, the block will slide, and this is what's known as the breakaway point. Where finally the pushing force overcomes the force of friction and the block begins to slide. And you can imagine, without too much, without working your brain too hard, you can see that the moment you pass the breakaway point, the moment you push hard enough to get this thing moving, now it becomes pretty easy to keep the block in motion. In other words, it seems as though after you overcome that initial bit of friction to get the block moving, the friction becomes less. And this is in fact true. While the block is at rest, these little bumps, right, these little ridges are allowed to really lock into one another very tightly. And so overcoming that initial friction, what we call the static friction. Overcoming that static friction is quite tough, but once you overcome that static friction, then the block is moving and the friction is significantly less, what we call the kinetic friction. And I have a little graph here that we can investigate this in some detail. This is sort of an interesting graph I found online on Google. And let's see what we've got here. This is an interesting plot. First of all, this is what's called the static region right here. So what's happening here is a force is being applied, force is being applied as we move along the x-axis. Force is getting bigger and bigger and bigger, right? The f-axis is F. And the y-axis is the frictional force. And so in the static region, in other words, the block isn't moving, right? It's static means not moving. As you push harder and harder and harder and harder and harder, the friction force grows at an equal rate. You push harder and harder, friction gets bigger and bigger at an equal rate. So there's this linear relationship between the pushing force and the friction force. Up until this point, this is the breakaway point, right? This is the point after which this is the maximum friction force right here, F max. And at this point, breakaway occurs, and now the pushing force exceeds the frictional force and the object begins to move. And look what happens. The friction force now, we're in the kinetic region, kinetic means moving, and now the friction force diminishes, and it actually diminishes quite rapidly. So now as you move the object, as you push harder and harder and harder and move the object, the friction force diminishes. Okay? And what's going to happen as the friction force diminishes, so now the pushing force F gets bigger, and the frictional force, little f, gets smaller. What that means is the F net is going to get bigger and bigger and bigger. And then this is interesting. What happens here? Now the block is moving, and we've got, right, it's bumpy here. What does that mean? Well, if the surfaces aren't totally smooth, that means that the frictional force is going to vary slightly with time. As you push the objects past one another, there's going to be sort of a constant change in the amount of friction. Some areas of the surface are smoother, and some areas are rougher, and so there's going to be some fluctuations to the amount of friction. So there's a little bit of roughness here. So that's a sort of an interesting graph that explores something that you probably have noticed in your everyday life, that in fact it's harder to get the object moving, and once you've got it moving, it's pretty easy to keep it going. And so let's investigate, how would you calculate the friction force? Well, it turns out that the friction force depends on only two things. The first one is obvious, the roughness of the surface. So the two things that determine the friction force are the roughness of the surface, which is represented by what's called the mu value. This is the Greek letter mu, M-U. And this is a coefficient that takes into account the relative roughness of the two surfaces. Okay, it's something that's determined experimentally, and you can look up mu values for any two surfaces, right? You could look up the mu value between sandpaper and wood, between metal and linoleum, whatever, and that would indicate the roughness of the two surfaces. And it's a coefficient. It has no unit. It's just a measurement of how much friction there is between the two surfaces. It can be very, very small. If you have two surfaces between which there's very little friction, it could be very small, like under something like 0.01. Or it could be quite large if you have two surfaces where there's significant friction. So mu, or the coefficient of friction, matters. Well, what else matters? This maybe is requires a little bit more thought. If I imagine putting my hands together, right, and rubbing my hands past one another, my hands have a certain mu value. It's pretty significant because of these ridges. But what else could I do to increase the friction? I could push my hands together more tightly, right? If they're pressed together harder, there's going to be more resistance to sliding. So what do I mean by pressed together tightly? Well, I'm speaking about the normal force. So the normal force matters as well. So F normal. So this is how hard the surfaces are pressed together. Okay, so normal force, F normal. And it turns out these are the only two things that matter, and so I can say that the friction force, F friction, do it down here, is equal to mu, the coefficient of friction, times the normal force, F normal. And that's all there is to it. This is the equation for friction. It's a pretty simple relationship. There's two things that matter. You multiply them by each other. But we have to take into account the fact that the amount of resistance, it changes depending on whether or not you're in a static situation or a kinetic situation, right up on the graph here. We have to take into account the fact that there's a difference between static friction and kinetic friction. And the way that works out, and you can actually see it, you may have noticed this, is that this guy right here says mu sub s, and this is mu sub s times big N is supposed to be the normal force. And this one says mu sub k times normal force. And so in fact there are two different types of mu. Okay? So there's a mu value called mu sub s, and then there's a mu value mu sub k. And mu sub s is the value that you use if you're in a static situation, if you have two objects that are at rest with respect to one another. Mu sub k is the value that you use if you know that the surfaces are in fact moving relative to one another. And the fact that the static friction is more than the kinetic friction is because mu sub s is almost always greater than mu sub k. I'm not familiar with any situation in which that's not true, but I don't know, maybe there's some wild situation where it isn't true. But in general, we say mu sub s is bigger than mu sub k, so the static friction is bigger than the kinetic friction. All right. Well, let's do a couple examples to investigate this. The first example, I'm going to use some numbers here. Let's imagine we have a flat surface. It's supposed to be flat. Here's the surface. And we've got a block on the surface. Some block M. And let's say that we're pushing this block with some force F. And there's going to be some frictional force that's going to act backwards, F friction. Okay. What other forces are there? Well, we've got the weight down, mg, and we've got the normal force up, F normal. Actually, maybe I'll, yeah, well, I guess we'll call this, we'll just stick with that as F. So let's give these, or let's give the problem some numbers here. Let's say the mass here that we're using, let's say that M has a value of 10 kilograms. And let's say that let's imagine it's a static situation and the coefficient of static friction, mu sub s, is 0.5. And let's say you push with a force, this is your pushing force here, F is 59 newtons. Okay? So the first question that you might ask yourself is, okay, what's going to happen? Is this F, is this 59 sufficient to get this static block moving? In other words, if you've pushed with 59 newtons, will this overcome the force of static friction? And we could test that out, right? If for this thing to accelerate, we need to have a net force. Okay, well, let's think about the net force. What forces are relevant here? Do we need to wonder about acceleration in the y direction, up and down? Hopefully you see that we don't need to worry about that, right? The normal force, F normal, is going to be equal to mg in this case. They're equal. And so there's no acceleration in the y direction. So the only forces we need to worry about are the pushing force F and the friction force F friction. Those are the only two forces we have to worry about. If F is bigger than the friction force, this thing will accelerate. It will break away. If not, if the force here, F, is the same size as the friction force, we're in equilibrium, acceleration won't occur, there'll be no breakaway. So the question is F bigger than F friction? Okay. Friction force, right, is not going to be bigger than F, right? If this is a static situation, the friction force is not going to cause acceleration in the opposite direction. So what we have to see is, are they equal, or is F bigger than F friction? By the way, maybe I should write this. F friction max, right? Is the pushing force bigger than the maximum possible value here. So let's investigate that. Let's see. So we know that the friction force is 59, or the pushing force, F, this is 59 newtons. So let's go ahead and calculate F friction. Well, that's mu sub S times the normal force. Well, what is the normal force? We already said it's equal to mg. So I'm going to say that the friction force is mu sub S times mg. That's 0.5 times mg is 9.8 times 10, which is 98. And this is a force here of 49 newtons. This is the maximum value possible for static friction. So is the pushing force bigger? Yes. 59 is bigger than 49. So breakaway will occur and this thing will slide. Now, I want to bear in mind, the moment this thing begins moving, if I then asked you what's the acceleration, you couldn't say, if we were trying to find the acceleration of the block once it was in motion, we could not say that the net force is 10. Why is the net force not 10 here? Because the moment this slides, mu sub S is no longer relevant. Then we'd need some mu k value, which would be smaller. Maybe it'd be something like 0.2, I don't know. And then you'd be in a kinetic situation and you'd have to find the new kinetic friction force. But I'm not going to ask that right now. I want to ask a different question. So let me ask a different question here. I'm going to erase this. Give myself a little bit of room. Same setup. But now I want to think about, I'm going to get rid of that. And I want to think about, okay, this friction force, or this pushing force, 59 newtons, will overcome the friction force in this particular case. But what could I do? Let's imagine I wanted to prevent this block from sliding. How could I prevent this block from sliding? Well, one obvious thing is, I might somehow push back against this pushing force. But let's ignore that for a moment. I want to think about how I could, in fact, increase the amount of friction in this case. How could I cause this value to go up? I can't easily change the mu value, right? I can't alter the roughness of these surfaces very easily. But there is a way that I can change the normal force. So that here, this is the normal force, right? There's a way I can change the normal force. And if you imagine, one thing you could do is you could push with some force P down. You could apply a force P downward on the block, and you could therefore push the block into the surface, thereby increasing the normal force. I want to think about why that works. Why is it that if you push down on this block vertically, straight down on it, you're increasing the normal force? Well, provided the table doesn't break, if you push down on the mass will not, again, accelerate in the y direction. Why not? Because when you push down, the table pushes up equally. So the normal force will automatically grow to match whatever the total downward force is. So in other words, what I can say is, I'll express it this way, F net y equals 0, which means now that the normal force is going to equal mg plus p, where p is my pushing force here. Automatically, this is going to happen because assuming that the table doesn't break, we can have no acceleration in the y direction. So the F net in the y direction must be 0. So this must now be true. So by pushing down on the block, I've increased the normal force. And by increasing the normal force, I've increased the friction. And the question I want to ask now is, how hard do you need to push? So what P value will prevent sliding? Right? We said that without pushing on the block down, without this P, the block will slide. But how hard could we push such that it doesn't slide? All right, well that means what we're looking for here is F net 0. If it doesn't slide, there's no acceleration. That means zero net force. So we need a situation where F net is 0, meaning mu times F normal must be equal to the pushing force F. So let me rewrite that, right? This is our situation. Okay, F net is 0. How do I know F net is 0? If A is 0, that means that F net must be 0. So the frictional force, the retarding force here, must be equal to F. So what is that going to look like? Well, that means that mu times the normal force. What's the normal force? We just said mg plus p must equal F. So what must p be? Well, let's go ahead and plug in some numbers and find out. So we're going to say 0.5 times mg is 98 plus p equals F. Sorry, we know what F is. F is 59. Now we can just go ahead and solve for p. So we get 49 plus 0.5p equals 59. So p equals 20 newtons. Okay, so hopefully you followed that algebra. What I'm saying there is that if you push down with some force P, you're increasing the normal force, and in this particular case, given these particular numbers, you need to push down with a force of 20 newtons to increase the frictional force to such a point where you'll maintain equilibrium and the block won't slide. One more, I know this is a longish video, but one more really interesting case I want to think about. Let's imagine now we've got a ramp. Here's this ramp, and it's angled at some angle theta. I'm not even going to give these numbers. I'm just going to go ahead and solve it without numbers. So here's theta, and we've got a block on the ramp. So here's this block. Let's go ahead and think about the forces that are acting on this block. Well, we've got mg acting down. We've got the normal force going up. And we've got friction now going backwards. I'm imagining that the block is at rest, right, on this surface. So we've got a friction force acting that prevents this block from sliding down. And what I'm interested in is what mu value in this case, what mu value will prevent sliding. Now I don't have any numbers, but I'm just going to sort of think about, in terms of the values that we're given, what sort of mu value would be necessary. So let's first go ahead and recognize that you can split mg into components, right? There's a component that is perpendicular and to the surface, to their plane, and then a component that is parallel to the plane. And since this angle here is theta, same as this angle, right? These angles are equal. That means that this here is mg cosine theta, and this is mg sine theta. Okay, and it might be actually helpful now to, I'm just going to erase that so that it doesn't clutter the picture. We've split up into its components and we can sort of ignore it now. So we've got this block now, and what I sometimes think it's helpful to take my axes, my x and y axes, and sort of turn them, which is a legal move, right? I can take my coordinate plane, and now I'm going to think of parallel to the surface as x, and I'm going to think of perpendicular as y. So I'm imagining now that this is, I've taken my axes and I've rotated them through the angle theta, so that I'm now thinking of this as my y-axis and this here as my x-axis. And provided that the plane doesn't break, we know that the normal force has to be equal to this force, mg cosine theta, because it's not going to accelerate in what I'm calling the y direction. So these two must be equal. So for this not to slide, I know that mu times the normal force, which is mg cosine theta, right? This is equal to mg cosine theta. Mu times mg cosine theta must be equal to this downward force mg sine theta. Okay, I'm recognizing the friction here. This force is mu times mg cosine theta. Well, I don't know what m know what m is, and I don't know what theta is, but one thing that we can see here is if we try to solve for mu, we get this. Mu equals mg sine theta over mg cosine theta. And this is an interesting result because you see m is irrelevant, doesn't matter. And we get that mu equals tangent theta. So the necessary mu value to prevent sliding depends only on the angle of the ramp. Okay, g is irrelevant. So this is kind of an interesting result. And if you imagine, if we were to make a graph here, if we were to plot tangent theta against theta for angles 0 to 90, right? We would get a graph that looks like this. It starts at 0 and it gets bigger and bigger and bigger and bigger and bigger and asymptotically approaches this point here. Meaning that the mu value, as you increase theta, there's not a linear relationship between how mu grows. As theta gets bigger and bigger and bigger, the mu has to get bigger at an increasing rate. So that's an interesting result. This particular picture will come in handy in a lot of practice problems. Okay, that's all for now. We'll have a chance to practice this next class.